All right, so the next problem is an optimization problem out of section 4.4, and it's number 23. It says a rectangular flower garden with an area of 30 meters squared. So I'm going to draw in a rectangular flower garden here. So there's my rectangle with an area of 30 meters squared, is surrounded by a grass border 1 meter wide on two sides and 2 meters wide on the other two sides. So let's go up here. This will be the 1 meter wide on the top and bottom maybe, and 2 meters wide on these two sides. So you got an extra 2 meters, an extra 1 meter, an extra 1 meter. What dimensions of the garden minimize the combined area of the garden and the borders? So the garden is what we're really concerned about. We're concerned about an x dimension, and we're concerned about a y dimension. The borders are always going to add 2 on each side of x and 1 on each side of y. So the constraint really is this. The constraint becomes x times y equals 30. So I have to get 30 meters squared out of those two. And at this point, I always like to get my area equation as a function of only of x. So I would like to maybe solve this for x. X equals 30. Oh, excuse me. Let's go back on that. I'm going to solve that for y so I can substitute in for y later. So y equals 30 over x. That's also my constraint. And now I want to work with the area. The overall area is what I'm really going to work with here. So the overall area would be x plus 2 plus 2. So x plus 4. And I would multiply that by y plus 1 on each side, which is y plus 2. And what I'm going to take is I'm going to take that y and I'm going to substitute it in for there. So I want to make this a function only of a of x. So it's going to be x plus 4 times the y is going to be 30 over x plus 2. Okay? And I can do that a little bit further here. A of x actually, take me a little bit further here. X times 30 over x is just 30. Plus 2x plus 120 over x plus 8. Now I've got my actual a of x, which is equal to 2x. And I'm going to do this 120 over x so I can take a derivative easily. I'm going to call that 120 times x to the minus 1 plus 38. I just think it's easier to take the derivative there. And I'm going to do a prime of x equals 2. So the derivative of 2x is 2. Derivative of 120 x to the minus 1 is minus 120. The negative 1 comes in front. X to the minus 2. So that'll be negative 120 over x squared. And the 38 just goes away. And so what I want to do with that now is I really want to set that equal to 0. I want to set that derivative equal to 0. So I'm going to take 2 minus 120 over x squared. I'm going to set it equal to 0. And let's see here. That becomes 120 over x squared equals 2. Just move the 120 over to this side and flip it. That's equal to 2x squared. Multiply x squared on each side equals 120. Take that a little bit further, and I get x squared equals 60. Therefore, x equals plus or minus the square root of 60. And in this case, the minus doesn't really do anything for me because that would be a negative number. And so if I just take the square root of 60, square root of 60 is approximately 7.74. Now you might say, well, is that a minimum? Is that a maximum? How do we know? Well, one of the ways you could do it is you could substitute in this equation. You could say, well, what's a prime of 5? what's the slope at 5? I find out it's negative 2.8. The slope at 7.74, which we just did, we know that that's a critical point. The slope is 0. And then you could find out what the slope is, let's say, at 10. Okay? And at 10, it's 0.8. So from this, we can determine that 7.74 is a local minimum. Okay? And then from there, we can calculate what the y is going to be. And we kind of knew this is our only critical point that really could do anything for us anyways. So now we can calculate the y, just going back to y equals 30 over x. Y equals 30 over x. So therefore, y equals 30 over 7.74. And therefore, x equals 7.74 from up here. And y, plugging in my calculator here, equals 3.87. Now you have an x term and a y term.